Germany has just crossed an important threshold in the development of its hydrogen economy. For years, Europe's green hydrogen industry has been dominated by announcements, planned electrolyzers, proposed pipelines, future industrial clusters, and ambitious national strategies. But this story is different. Hydrogen produced through electrolysis in Lingen, Lower Saxony, has now traveled through approximately 120 kilometers of pipeline infrastructure and reached Marl Chemical Park in the northern Ruhr region. That means three critical parts of the hydrogen value chain have operated together: hydrogen production, pipeline transportation, and industrial delivery. The question is no longer simply whether Europe can produce renewable hydrogen. The real question is whether Europe can connect producers, infrastructure operators, and industrial customers at sufficient scale, and whether Germany's emerging network could become a model for the rest of the continent. This is a central milestone. Hydrogen is physically moving through the network. During the commissioning of the electrolyzer facilities in Lingen, initial quantities of renewable hydrogen were produced and prepared for pipeline transportation. That hydrogen entered infrastructure operated by several network and industrial partners. It then traveled through the connected pipeline system and became available at Marl for industrial production processes. This may sound like a simple delivery, but it represents something much larger. Electrolyzers, metering systems, pipeline operators, control systems, and industrial receiving infrastructure all had to function together. Germany is moving from testing individual pieces of hydrogen technology toward operating an integrated system under real conditions. Europe has spent years focusing heavily on electrolyzer capacity. Governments have announced gigawatts of planned production. Manufacturers have expanded factories. Developers have identified renewable energy sites. But an electrolyzer operating in isolation does not create a hydrogen economy. Hydrogen must be conditioned, compressed, measured, transported, and delivered to a customer prepared to use it. Without those connections, even a technically successful electrolyzer can become a stranded asset. A producer may generate hydrogen, but if there is no pipeline, storage system, transport agreement, or industrial customer, the molecule has nowhere commercially useful to go. That is why the Lingen to Marl connection matters. It begins to address the infrastructure gap between production announcements and actual industrial consumption. A functioning hydrogen economy is not one machine. It is a chain of interconnected systems. Renewable electricity must first reach the production site. Water must be purified to quality required by the electrolyzer. Power electronics must convert grid electricity into form needed by the electrolyzer stack. The hydrogen must then be separated, dried, tested, and delivered at the correct pressure. From there, it must enter a pipeline network, move safely across the region, and arrive at an industrial facility with compatible equipment and sufficient demand. Every component depends on the others. A delay in grid connection can delay the electrolyzer. A missing customer can undermine the pipeline. A pipeline delay can strand the production plant. Germany's emerging network demonstrates why hydrogen development must be approached as one coordinated infrastructure system. The journey begins at the energy site in Lingen. Lingen has historically been associated with major conventional power infrastructure. Today, the location is being repositioned as one of Germany's most important hydrogen development sites. Large electrolyzer facilities are being developed at the location, with further expansion planned as the regional hydrogen market grows. This concentration of power infrastructure, industrial land, technical expertise, and access to pipeline networks gives Lingen a strategic advantage. It shows why many early hydrogen hubs are emerging around existing energy and industrial locations rather than being constructed entirely from scratch. The old energy system is not simply being abandoned. Parts of it are being transformed to support a new hydrogen economy. The process begins with electricity. Renewable electricity enters the hydrogen facility through high-voltage grid infrastructure, substations, transformers, and power conversion equipment. Electrolyzers generally require controlled direct current electricity, so power electronics must convert and regulate the incoming supply before it reaches the electrolysis stacks. This stage is central to the economics of green hydrogen. Electricity is normally the largest operating cost component, meaning that the price, availability, and renewable qualification of the power supply can strongly influence the final cost of hydrogen. The electricity must also satisfy regulatory requirements if the hydrogen is to be classified and certified as renewable. Producing hydrogen is therefore not only about installing an electrolyzer, it begins with securing the right power supply. Inside the electrolyzer, electricity is used to split water into hydrogen and oxygen. Purified water enters the system and is distributed across multiple electrolyzer stacks. Within each stack, an electrochemical reaction separates water molecules. Hydrogen is collected on one side of the system, while oxygen is produced on the other. At industrial scale, this process requires much more than the visible electrolyzer stack. It also depends on pumps, water purification, heat removal, gas separation, electrical control systems, ventilation, safety detection, and process automation. The stack may be the technological center of the plant, but the surrounding balance of plant equipment determines whether the facility can operate reliably and continuously. This is why developers must evaluate the complete system, not only the electrolyzer's headline capacity. Hydrogen leaving the electrolyzer is not automatically ready for transmission. It may contain moisture, residual oxygen, or other trace impurities that must be removed before the gas enters the pipeline. The hydrogen therefore passes through separation, drying, purification, cooling, and analytical equipment. Operators must confirm that the gas meets the pipeline's required specifications. Moisture must be controlled because it can affect equipment performance and contribute to corrosion or operational problems. Purity matters because industrial customers may require specific hydrogen quality for their production processes. The gas temperature and pressure must also be stabilized. This conditioning stage is often hidden from public view, yet it is essential. A hydrogen network can only work when producers, pipeline operators, and customers agree on a consistent, measurable product specification. Once the hydrogen has been purified and conditioned, it must be delivered at the appropriate pressure. Compressors increase the pressure so that the gas can enter the pipeline and move through the network. This process requires energy and specialized equipment. Hydrogen's small molecular size, low density, and physical properties create different engineering requirements from conventional natural gas systems. Compressor materials, seals, valves, and monitoring instruments must be appropriate for hydrogen service. The station must also manage temperature increases associated with compression and ensure that pressure remains within the pipeline's operating limits. Compression is therefore both an engineering requirement and an economic consideration. Every additional unit of compression consumes electricity, affects operating costs, and influences the overall efficiency of the hydrogen delivery chain. At the injection station, the production facility connects to the wider transport network. This is where ownership, responsibility, and measurement become especially important. Before entering the pipeline, the hydrogen is checked for purity, pressure, flow rate, and other quality parameters. Metering equipment records how much hydrogen is being delivered. Control valves regulate the flow, while isolation systems allow sections of the network to be safely shut down when required. The injection point also represents a commercial boundary. The producer must demonstrate that the hydrogen meets the network operator's technical and regulatory requirements. The network operator must then transport the hydrogen safely and account for its movement through the system. These procedures are essential foundations of a future hydrogen market. The hydrogen traveled through a network of approximately 120 kilometers between Lingen and Marl. This physical distance is important because it demonstrates more than on-site production or a short experimental pipeline. It connects two separate industrial regions across a broader transport corridor. The companies involved had to coordinate pressure, gas quality, dispatch, network access, and operational responsibilities. The route also forms part of a larger system that is still expanding. Additional pipelines are being completed or converted to connect storage facilities, more industrial customers, and other hydrogen production sites. The 120-kilometer delivery is therefore not the end point. It is an early operating section of a much larger planned hydrogen network. Most people traveling across the region will never see the hydrogen infrastructure beneath them. Pipelines pass under fields, roads, waterways, and communities with relatively little visible impact above ground. This invisibility is one of the major advantages of pipeline transportation, once constructed or converted. A pipeline can move large quantities of gas continuously without requiring fleets of trucks. But invisible infrastructure still requires extensive engineering. Pipeline operators must monitor pressure, flow, and gas quality across long distances. They must protect the system against leakage, accidental damage, and unauthorized excavation. Valves divide the route into manageable sections, while control centers monitor operations in real time. The hydrogen economy may be symbolized by electrolyzers and wind turbines, but much of the system's real value lies underground. Germany does not intend to construct its entire hydrogen network from new pipelines. A significant portion can come from the conversion of existing natural gas infrastructure. Conversion can potentially reduce cost, land disturbance, and development time. However, it is not as simple as changing the gas inside the pipe. Operators must assess pipeline materials, welds, seals, valves, compressors, pressure ratings, and monitoring systems to confirm hydrogen suitability. Some sections may be suitable for conversion, with limited modifications. Others may require substantial upgrades or complete replacement. The ability to reuse existing infrastructure could become one of Europe's strongest advantages in scaling hydrogen transportation. Instead of beginning with an entirely blank system, Europe may be able to transform parts of the network already has. Industrial customers do not simply need hydrogen. They need hydrogen delivered within a defined technical specification. Purity must remain within agreed limits. Pressure must be sufficient for the receiving facility. Flow must be measurable and predictable. Customers may also require documentation proving the hydrogen's renewable origin and sustainability characteristics. This introduces a digital and regulatory layer to the physical molecule. The customer is not only buying hydrogen, it may also be buying verified renewable attributes, emissions reduction value, and regulatory compliance. A scalable market therefore needs trusted measurement and certification systems alongside the pipeline itself. Without consistent quality and credible documentation, industrial users cannot confidently build hydrogen into their long-term operations. At the end of this initial journey is Marl Chemical Park. The arrival of hydrogen at Marl is significant because the site represents concentrated industrial demand. Chemical parks contain multiple processing facilities, shared utilities, pipe racks, storage systems, and large quantities of industrial feedstocks. Hydrogen arriving through the pipeline can be made available directly for production processes at the site. This is fundamentally different from building an electrolyzer and hoping that future customers eventually appear. The infrastructure has been developed around identifiable industrial users. The Marl connection also increases the site's attractiveness to businesses that may require access to renewable hydrogen. In this way, the pipeline becomes more than a transportation asset. It becomes part of the industrial development strategy for the entire region. Hydrogen production receives much of the attention, but demand determines whether the project creates lasting value. An industrial customer must have equipment capable of receiving and using the hydrogen. The customer must also have a business reason to switch from its existing fuel or feedstock. That reason could include emissions targets, regulatory requirements, carbon costs, customer demand, or access to financial support. However, renewable hydrogen may remain more expensive than conventional fossil-based alternatives. Industrial users therefore need confidence in long-term supply, price, and certification. The Lingen to Marl system shows the importance of developing customers and infrastructure alongside production. The project becomes credible because the molecule has a route, a destination, and a practical industrial application. The objective is not simply to add more hydrogen to the economy. The objective is to replace hydrogen and fossil fuels associated with higher emissions. Industry already consumes large quantities of hydrogen, particularly in refining, chemicals, and fertilizer production. Much of that hydrogen has historically been produced from fossil fuels. Renewable hydrogen can contribute to decarbonization when it replaces its existing high-emission supply or enables lower-carbon industrial processes. But substitution is not automatic. The renewable hydrogen must be delivered reliably at the necessary quality, and at a price the industrial user can manage. The receiving process may also require modifications. The true measure of success is therefore not the electrolyzer's capacity alone. It is the quantity of conventional energy or fossil-based hydrogen that is actually displaced. The GET H2 nucleus is designed as a connected regional hydrogen cluster. It brings together hydrogen production, pipeline operators, storage infrastructure, and industrial users across Lower Saxony and North Rhine-Westphalia. The infrastructure is intended to expand in stages. New and converted pipeline sections can connect hydrogen production sites with storage facilities and additional industrial customers. This cluster approach reduces the risk of starting with a nationwide system all at once. Germany can begin with concentrated supply and demand, establish operating procedures, and then connect the cluster to a wider network. This is how infrastructure systems often scale. They begin with a strong local connection and expand as more producers and customers join. The Lingen to Marl connection is only one section of Germany's broader hydrogen strategy. The planned hydrogen core network is intended to connect major production, import, storage, and consumption locations across the country. It will progressively link regional clusters and provide connections toward neighboring countries. The aim is to create a national backbone rather than connect every individual customer directly. Regional and local networks can then branch from this backbone toward industrial parks, steel plants, refineries, chemical facilities, and other demand centers. The challenge is enormous. Large amounts of capital, regulatory coordination, construction capacity, and customer demand will be needed, but the first operating corridors provide a practical foundation for wider expansion. Hydrogen is most likely to scale first in industrial clusters, where several important conditions already overlap. There must be substantial demand. There must be access to renewable electricity or hydrogen imports. There must be suitable land and permitting conditions. There must also be pipelines, storage, or other transportation options. Industrial clusters can share major infrastructure rather than requiring every company to build a completely independent system. One pipeline can serve multiple customers. One storage facility can support several producers and users. Shared systems can improve utilization and reduce the cost per unit of hydrogen transported. This is why ports, chemical parks, steel regions, and refinery corridors are becoming early centers of hydrogen development. The geography of supply and demand matters as much as the technology. A pipeline is valuable only when customers use it. Hydrogen networks require large upfront capital investment, but early demand may develop gradually. If only a small volume moves through a large pipeline, the cost allocated to each unit of hydrogen can be high. Network operators therefore need credible forecasts and increasingly firm commitments from producers and consumers. Industrial customers may be reluctant to sign long-term agreements before hydrogen prices are clear. Producers may be reluctant to build before pipeline access is guaranteed. Pipeline operators may hesitate without confirmed supply and demand. This creates a coordination problem. Breaking this circular dependency is one of the central challenges facing hydrogen infrastructure worldwide. Early hydrogen networks may need to be built before they are fully utilized. That creates a difficult financial question. Who carries the cost during the market's early years? If the entire cost is immediately passed to the first customers, hydrogen transportation may become prohibitively expensive. If network operators carry the risk alone, they may struggle to finance large-scale infrastructure. Governments may therefore provide grants, guarantees, regulatory support, or mechanisms that spread repayment across a longer period. Public support can help establish the first infrastructure, but long-term sustainability will still depend on real commercial demand. The network must eventually attract enough producers and customers to support its operation without permanent dependence on public funding. For project developers, the most important lesson is that bankability is created across the entire system. First, the project needs reliable and qualifying electricity. Second, it needs an adequate water source and treatment process. Third, the electrolyzer and balance of plant systems must operate at the expected performance. Fourth, the project needs access to transportation and storage infrastructure. Fifth, There must be a customer with credible demand and an agreement that supports financing. Finally, the project needs a financial structure that can manage construction risk, operating risk, electricity price exposure, and market uncertainty. A weakness in any one of these areas can undermine the complete project. Hydrogen development is therefore not primarily an equipment selection exercise. It is a coordinated development of power, water, technology, infrastructure, customers, and finance. Can Germany's approach be replicated across Europe? Potentially, but not by copying every component exactly. Different countries have different renewable resources, pipeline systems, industrial concentrations, and regulatory structures. The transferable lesson is the sequencing. Begin with regions where hydrogen production and industrial demand can be connected efficiently. Reuse existing infrastructure where it is technically appropriate. Develop storage alongside transportation. Create clear rules for network access, certification, and capacity booking. Secure early industrial customers before expanding too far. Then connect successful regional clusters into national and cross-border corridors. Germany's experience may therefore serve less as a fixed blueprint and more as a systems development model for Europe's emerging hydrogen economy. The most important development is not simply that hydrogen was produced in Lingen. It is that renewable hydrogen moved through a multi-operator pipeline network and reached an industrial customer in Marl. That is what separates a technology demonstration from an emerging market system. Europe will not scale hydrogen through isolated electrolyzers, disconnected pipelines, or industrial promises made independently of one another. It will scale when production, infrastructure, storage, regulation, finance, and demand operate together. Germany has not completed its hydrogen economy. Commercial operation, network expansion, customer commitments, and competitive costs remain major challenges. But the Lingen to Marl connection shows that the physical system can work. The next question is whether Germany and Europe can expand this early corridor into a reliable, affordable, and commercially sustainable hydrogen network. Explore the projects, technologies, equipment, and development pathways shaping this market at h2hub.renenergy.com.